Good evening and welcome everybody. It's Obi-Wan Pez for N Simplex Pachinko. We are going to be doing some mathy stuff tonight with cracking the GRE math subject test. Woo! Coming up on the end of the Calculus 2 final exam type thing. Thank goodness. Getting pretty close to the end of it. So, then we'll be starting in on multivariate calculus, also known as Calc 3 in many places. Amusingly, it is called Calculus 2 in this book. Oh, man. Hope y'all are having a good evening. Anyway, we are also working with Go Tell, Game On to End Lupus. You could see the banner all the way at the top or the QR code down below. These are places to donate if you have the means and interest to do so. Lupus is an autoimmune disorder which wreaks havoc on people's lives. It does terrible, terrible things to the human body, and we're trying to raise some money for awareness and research. The Lupus Foundation of America is the organization putting on this Go Tell event. We're also working with 8-Bit D, Coco Confession, L-Bell, and many others who themselves have lupus or other autoimmune disorders. So, trying to help people out, do some good in the world. And if anybody's interested, we have some incentives. You should be able to see some incentives on the site. There are individual donation incentives, and then there are goals for the entire campaign. This is for the entire month of May, so we'll be continuing to do this up until 31st. I am also on vacation one of those weeks, now that I'm thinking about it. 31st is a Sunday. Okay. Well, 29th anyway. I believe we are gone the week of the 25th. Or, I guess, somewhere in there. Yep, so family and I are headed to Croatia. Ought to be really interesting. Everybody really talks about the beaches at Split, so looking forward to checking stuff out. Okay. So, to continue on our you know what, let's actually push this out just a little bit further. Not that one. Push that out just a little bit further. So we can be, roughly speaking, even with the control bar here. Okay, so question number 39. Find the positive value for a, which satisfies the following equation. So we have the integral that goes from 0 to a of dx over square root of a squared minus x squared equal to integral from 0 to a of x dx over square root of a squared minus x squared. Okay, so I think the good news here is that these integrals should just be inverse sine and inverse cosine. I hope. Okay, so if we were to be a huge pain in the rear, we could say that what we've got is x squared on the long, no, wrong, incorrect. We're going to have a as the hypotenuse length. Reason being, right, this term at the bottom is a squared minus x squared. In a Pythagorean theorem, that would be a being the hypotenuse would be the largest one. So a squared minus x squared needs to be a positive number because it's inside the square root. So yeah, a is going to be there. X is going to be either of the legs. It really doesn't matter. And then the bottom is going to be a square root of a squared minus x squared. Okay, so what we have here as it sits, right? This would end up x goes from 0 to a. This would end up being tangent of theta, being x over square root of a squared minus x squared. And then dx in terms of d theta would be a little bit more interesting, unfortunately. That would mean that x is equal to, well, x over a is equal to the sine of theta. Or x equals a sine theta. Therefore, dx would be equal to a cosine theta d theta. Which means we get an a times cosine theta d theta, d theta, not dx, because that literally just replaced that. Tangent is sine theta over cosine theta. So this cleans up rather nicely. This is going to be x from 0 to a. Tangent is sine over cosine. So cosine multiplied by 1 over cosine is just going to get us, in this case, a sine of theta. D theta. Now that is a very straightforward type of equation. Works out very nicely. Okay, similarly, if we assume that the exact same triangle is going to be used for both of these, right, why not? It's the same situation that we have, really. This is just going to be here Again, let x equal a sine theta. Just a reminder, right? Dx is going to be equal to a cosine theta d theta. And so on this side, what we're going to end up with is the secant of theta is going to be equal to a over square root a squared minus x squared. So secant of theta over a is going to equal 1 over root a squared minus x squared. With that, we also have dx being a cosine theta d theta. So, with the two things taken together, right, x goes from a 0 to a, and then we have here secant of theta over a multiplied by a cosine theta d theta. Okay, our a's are going to divide out, our cosine is going to divide out with a secant, and then we're just left with the integral as x goes from 0 to a of d theta. And that's it. So on the left, this is going to be theta, taken as x goes from 0 to a. And on the right, we're going to have a negative a times cosine theta as x goes from 0 to a. For some reason, that really bothers my ears. Don't understand. Okay, so from here, theta is just going to be, well, this is x over a equals sine of theta. Therefore, theta is going to be the inverse sine of x over a. Taken as x goes from 0 to a. We'll talk about that in a second. Then here, the cosine of theta, right, is going to be negative a times cosine is root a squared minus x squared all over a. Our a's are going to divide out nicely. Evaluated where x goes from 0 to a. Okay, here we have the inverse sine of a over a is 1 minus the inverse sine of 0. It's going to be equal to negative. This is going to be the square root of a squared minus a squared. Right, minus a negative makes a plus. And then here it's going to be square root of a squared minus 0 squared. So just that. Okay, so a is on the right, and on the left we're going to have the inverse sine of 1. The inverse sine of 0 is just 0. Inverse sine of 1 is pi. So a should be pi. And that's not an option. Cool. So, where else do we screw up? Oh, no, it isn't. No, it isn't. A is inverse sine of 1 is going to be the maximum height that it is, so that's pi over 2. Oi, that is an option. Silly mistake. All right, good news. Easy fix. Problem appears to be between book and keyboard. So, all right, so A was 2 root 2 over pi, B is 1, C is pi over 2 root 2, D is root 2, and E is pi over 2. So E was our choice for this one. Yay, trig sub. All right, so 40. Which of the following improper integrals converge? So 1, 2, and 3 are going to be our 3 possible integrals. And then we have one only, 1 and 2 only, 2 only, 1 and 3 only, 2 and 3 only. Okay. Without even looking at, no. So, number 1 is integral from negative infinity to infinity of dx over x squared plus 1 parentheses all squared. 2 is the integral from 1 to infinity of x e to the negative x dx. Number 3 is the integral from 0 to 2 of dx over 2 minus x squared. So, which of the following improper integrals will converge? I'm pretty sure the first one will. We could go with a few different things, but this would be easy enough to do a comparison to a p-test of x to the fourth, or I guess we would compare it to the sum of I to the 1 over I to the fourth. So doing a p-test, 1 over I to the 4th. Converges. And 1 over I to the 4th will be greater than 1 over x squared plus 1 parentheses squared, because all this stuff is x to the 4th plus 2x squared plus 1. So these are all greater than 0. Okay, for all x in integers, positive integers, right? And actually, it doesn't matter, right? This can be just integers, doesn't have to be positives only. Right, so it's greater than 0 and it's in the denominator. So it's going to make the overall fraction smaller. Another way to look at it would be to say if we have something like this, we've got I to the 4th, looks roughly speaking something like this, and our continuous function is going to look something like this. X squared plus 1. Does that... It sort of messes with it a bit, but I don't think it's significant. Oh, right, we can do it in Desmos, because that's right here. Right, so 1 over x to the 4th. Change... Oh, right, that goes asymptotically. Fun. Right. 1 over parentheses x squared plus 1 squared. Right. So 1 over x to the 4th then doesn't quite do that, right? It goes up infinitely. But either way, that doesn't matter here. Good news. that one. Right, so because of this, over I to the 4th is greater than 1 over x squared plus 1 all squared for all x being integers. Then I goes from 0 to infinity of 1 over I to the fourth times a width of 1. So essentially we're making it like a Riemann sum in this stuff here. Alright, same's going to happen over here. This is also going to be 1, etc., etc., etc. It will be greater than the sum of j goes from 0 to, technically we want that as n, and then we're limiting because then it's going to be the limit as n goes to infinity, but honestly it's not going to matter all that much. 1 over x sub j squared plus 1 parentheses all squared. Okay, so that means that the sum as I goes from 0 to infinity, I can't do 0. Damn. 1. Of 1 over I to the fourth greater than, this is the integral of 1 over parentheses x, well, x squared plus 1 parentheses squared dx. And this would be delta x sub j as well. Okay, this would go from we can make this, we can kind of contrive this so that it goes from 0 to infinity, and it's going to also, do area of this thing plus the sum here. So it's at least comparable in the x direction. We don't have to worry about accidentally missing like a particular rectangle or something like that. Then this would mean that twice a0 plus this sum is also going to be greater than the integral going from negative infinity to infinity because this is symmetric. All right, 1 over parentheses x squared plus 1 and squared dx. So this improper integral number 1 will converge. Number 2. Right. Integral going from 0, 1. 1 to infinity x e to the negative x dx. Okay, so y only 1. Okay. So we have a uniformly decreasing function after 1. Before that, we do have a bit of a increasing function, which you could probably find. You could probably find some sort of sum to make this one work, like the earlier stuff between 0 and 1. But what we're mainly concerned with is again, the fact that this is going off toward infinity, and this is not a particularly obvious comparison. There's probably an easier way to do it, but if we're doing algebra, then we could do integration by parts and say that u is going to be equal to x, so du is going to be dx. And then dv is equal to e to the negative x dx, which means that v is going to be equal to negative e to the negative x. So x e to the negative x taken from 1 to b. We're going to take all these as the limit, as our limit of b is going off to infinity of everything from here on out. Minus integral from 1 to b of v du. So that is negative e to the negative x dx. Limit as b goes to infinity of b e to the negative b minus e to the negative 1 minus, well, okay, plus. The integral of e to the negative x dx is going to be negative e to the negative x. Okay, and that is going to go from 1 to b as well. B to the negative b minus e to the negative 1 minus e to the negative b plus e to the negative 1. Well, that's unfortunate. Right, so this is going to go to 0. B e to the negative b. Technically, we can't figure this one out by itself, so we'd want to do L'Hopital's rule. This would be e. Now, you know what? This would be b over e to the b. Which is going to be the same as the limit as b goes to infinity of 1 over e to the b. All right, take the derivative with respect to b as a variable in this case, or go back a few steps and do it in terms of x or whatever we feel like. It's all good. Okay, so that's the same number. Okay, and then minus e to the negative b. So this is all going to equal 0. Which does not actually make sense for the question. All right, what do we do wrong? So, error correcting moment here. Got to look it up. Got to figure out what it is that we did wrong. Input set. Hello. Just know that it's gamma 2. That'd be great, but we are supposed to be doing this from the context of a Calculus 2 class. So they haven't even studied Taylor series at this point. Actually, that's not true. They would have studied Taylor series over the course of the entire semester. But in terms of the material that's a part of this test, they would not know Taylor series yet. And yeah, I know gamma is not in there, but gamma function would not be part of the whole curriculum. So, yeah. So yeah, what do we do to mess this up? Because this has a finite positive integral from 1 off to infinity, provided that it didn't just randomly like duck beneath 0, which no, right? It's exponential. It's starting above starting above 0, so it can't have anything but a positive value. So like, what about e to the negative x, right? Nope. That could prove that it diverges after 1. That's not going to prove that it converges. Okay, so, right, x is always going to be larger. Right. I'm very hesitant to move this, but... Ooh, no. Yep. There's a speaker back there. It does not want to move underneath the windowsill for some reason. It's so weird. And now we're tipping something. Alright. This is fine, I'm sure. Oh, yep. That's not okay. That's that one. The serial port is getting yanked upward. Oh man, yep. Lifting the entire tower. Off the ground. Okay, there we go. That's probably as much as I want to actually lift this thing up, but that's all right. Okay. So in theory, the only thing that we could really do here is show that if e to the x were to diverge, then x e to the negative x would also diverge. But that's not going to happen. All right, e to the negative x as an integral is going to converge, but then x e to the negative x is above that. So we can't have any conclusive testing done. Okay, so what else can we do? What are the other integral tests that we keep doing? Right. What are some of the other integral tests? Improper integrals, infinite series, alternating, no, okay, so we could do potentially ratio. Comparison. If f of x is a positive monotonically decreasing function for x greater than or equal to 1, such that f of n equals a sub n for every positive integer, and then it would be sufficient to show that if the series converges, then the integral will converge. I mean, okay. So, same deal anyway, right? We're gonna attempt to say, okay, we don't have this. None of that worked. Right, so or 1 to infinity, I suppose. Okay, this is going to be I times e to the negative I. Delta x sub I. So by ratio test, we say what's going to happen when we take I plus 1 times e to the negative parentheses I plus 1 and compare it with I times e to the negative I, and we want the limit as this goes off to infinity. Okay, so what we get here is going to be I plus 1, well, okay. I goes to infinity of I plus 1 over I, which is just going to be 1, so that's kind of boring. Okay, multiply by limit I goes to infinity of e to the negative parentheses I plus 1 over e to the negative I. So when we shift those around, that's going to end up being the limit as I goes to infinity of 1 over e. Should just be 1 over e. Right? So that's going to be e to the I divided by e to the I plus 1. So there's just 1 extra in the denominator. So yeah, it's this. And then technically, yeah, we need absolute value or whatever. It's fine. Okay, which is less than 1. So this converges. Right? I think that's what we got. Yep. So integral from 1 to infinity of x e to the negative x dx will converge. So that's number 2. Okay, so number 3 is not going to converge because this is going from a finite value up to the infinite value. So there's 2 ways that we can do this. One is to look directly at this stuff. And then we say, like, this is going off to infinity as we get closer and closer and closer to the x value of 2, which is a problem. Or we'll look at it from the other variable's perspective. So like y equals 1 over 2 minus x parentheses squared. This would end up as the square root of y is equal to absolute value of 1 over 2 minus x. This would be 2 minus x, absolute value is equal to 1 over root y. Here in this particular case, right, what we want is the stuff that's between 0 and 2. So this will end up with positive values only. Or non-negative, I suppose, because we could, in theory, get 0 as well. So yeah, 2 minus x is equal to 1 over square root of y. This is x equals 2 minus 1 over square root of y. And if you notice, this is a p-series. P is going to be greater than -1. Right, with the exponent, or a sub n, it's fine. Right, and in the discrete case, this is also the case where we're going to have a p-series that fails to converge. Or diverges. This way, y that way, or x this way, y that way. Deliberately. Nope. So close, but no. There we go. So 1 and 2 only. Which is going to be B. And again, 3 fails. So we're not able to converge using number 3 because, again, we could look at it as a p-series in the opposite direction. I to the p in this particular case is going to be, p is going to be -1/2. So that's going to be greater than -1, and so the series fails to converge. The series diverges, whichever way you want to say it. It all works. And then cool. That's number 40. Number 41. We're going to go and bring that stuff. Dishes downstairs. I recommend everybody go and stretch, get up, walk around, do something like that. And we'll be back in roughly 3 minutes when ad break is over. Thank you so much, everybody, for coming. Again, the Go Tell links, Game On to End Lupus. There's a QR code down there, and our banner up there is just for information. If you would like to donate, that'd be awesome. Again, lupus is an autoimmune disease, affects a lot of people, and right now, GoTel is raising money in order to fund help for people as well as research, because we need a lot more. So anyway, I'll see you all in 3 minutes. Thank you so much for coming. Righto, welcome back. Right, let's do the hard thing and try to do some Tai Chi in this tiny area. So, righto. Our usual warm-up is just gonna swing the hips back and forth and then let the arms come up. We're essentially putting a little bit of energy into them like kids on a swing. Rotating at the hips and tucking into the inguinal crease in the groin area. Just kind of let it twist in and then push out. Push your body out of that, like, out of that twist. So when you twist into it, you can feel like your upper thigh and your abdomen kind of come together a little bit. Then come back out by just pushing some of your leg muscles, and it kind of can let your kind of puts a little extra energy into your arms moving back and forth. Terrible at describing this. It's all right. All right, now we do this to the front as well. Here, just kind of bend the knees a little bit, and the arms go flying. Really good for getting the synovial fluid in between all your joints moving. And helps warm up the muscles. Backwards and forwards, like we're skiing. Again, just kind of get the hip motion into it a little bit. And then if we put one leg forward, one leg back, we can also go like this. Again, swinging, letting the arms swing as they may. You're just adding a little bit of energy into them by essentially pumping like you're on a swing. Not too much, otherwise they flop. And we don't want that. Right. So, Tai Chi form. We start this bear pose, feet together in shape of a V. And then from here, we tuck into the right inguinal crease, move the left foot out, and then straighten out the right foot as we recenter. Breathe in for 2, out. We create the kind of energy ball here. This is the typical thing that you learn about in Tai Chi. Create this like energy ball. It isn't really energy. And tuck into the left inguinal crease, and then we step with the right foot, and we go out, and then we from here switch and move the left foot forward and twist in. This is a ward off here. Our right hand is sort of hanging loose but forward to make sure that we're in the right, we have the right structure. It's a little bit like if you've done ballroom dancing, you need to have your structure in, otherwise the frame, there we go. You need to have your frame in, otherwise you start like doing weird stuff and your partner doesn't know what you want. Then, since we're leaning forward on the front leg, we take our back leg and twist at the balls of the feet, and then take a step as we swap into ward off, lock everything in, do a roll back, press, and then push. When we come back to leaning on the back foot, then we shift so that we're now pigeon-toed, essentially like this. The hands come forward, they drop in, and we put a lot of tension on the front foot until, because we're turning, like our hip just has to turn at the balls of the feet, and we do a single whip this way. We step out with the left and hold block this way. And then as we shift our weight to the front leg, we're also going to turn the front hand and also rotate the foot into place. And then we do lift hands, so everything comes down and then comes back up to the front. We bring everything back in, and then we do a shoulder strike. And then we twist, let's see. So we're doing tuck into the right inguinal crease. When we do this, we also shift our left foot is going to be rotated on the heel to come forward. And then from here, we step with the left foot and do white crane. Almost all of our weight is on the back foot. The toes on the left foot, the front foot are just barely touching the ground. From here we do what's called brush knee. So our hands come down, do a double circle block, and then we step in, allowing the force to be transferred through the body into the hands. Right, then from here, totally don't need more space than this. Right, we do a what's called strum the lute. So we have to stand basically feet 90 degrees together. Our hands are going to reverse places and then come into, it's basically the same as lift hands, ever so slightly. Then once we're in strum the lute, we do another brush knee here. And then we lean back on the left heel, close the fist and bring it forward while we turn 45 degrees to the side. From here, we step through with the right foot, turning completely 90 degrees the other way. And then as we step through, we bring the other hand through and punch. Okay, from here, then we're going to do Rufeng Subi, which is tucking into the left inguinal crease, bringing the left hand underneath. We take if somebody's either grabbing our wrist or putting some sort of pressure against us, we take our left hand, shunt it underneath, and take that pressure off. So we take that with the left, and then from here we lean back and do a push. Lean back again, come back to the front. Again, pigeon-toed. our left foot is straight, our right foot is like cocked way off to the side. So we take the right foot and we straighten it out as we come around. We're still resting mostly on the left foot, and then our right hand is kind of taking most of the weight of the left hand. And we just kind of keep it right here. And my instructor said we also keep enough room under the elbows, kind of like pushing up and out just a little bit. Okay, from there, that's like the first third of the form. Woo! Then we come in like this. This comes back around the ear. Our right hand is down next to our knee. And then we take a large 135-degree angle, so 45-degree angle backward step this way. And then as we turn from here to there, we end up basically throwing or striking out in this direction. Then we switch to a right rollback, press, push, lean back again, and then we whip around this way. Again, the left foot is all like twisted, so as we keep turning this way, we do another single whip, and as we do that, we turn 45 to the corner of the room, lean forward, twist the hand, and change the back foot to better position. All right, then as we lean back, this time we turn our front foot perpendicular to the wall. This hand kind of lets go, and then we're going to essentially slap. We're going to essentially slap through, and then as we come through slapping like this, we're going to step forward and then take another step, again coming through with the power inside the hand. So it's going to be like all of our weight, our momentum is coming through into that hand. And the left foot is heel down on the ground, toes up in the air. And then we're going to break from here. Left hand comes back around to the ear. We take a straight step back, toes first, then heel, and then both the hand comes forward and the lower hand comes out this way. This is repulsing monkey. Then we hold this in front of us, put this back here, do the same thing. So we step backward, toes first, heel second, and then pop. And then we do it one more time. I don't have enough room really, but you know. Which way are we? We're this way. Nope. Okay. Then we take this and we rotate as we twist into the hip. We take another 45-degree angle step back that way. And went that way. As we turn this way, this hand, I did it wrong. Man. we should have been this way, twist around this way, because as we twist back here, we're going to press out. The right hand is going to contact somebody and basically push them this way. The idea is that you hook your foot behind their leg and then you shove them this way so that they're now going to be moving over your leg And if they try to grab your arm, you just basically pull your arm away. Whereas if you go this way and they grab your arm, you're going with them. All right, so here, then we curl into, again, energy ball here, take a left step, lock into cloud hands, and then come through, swap, step, oh, hang on, step, swap, turn, step, swap, turn, and then it goes forward. Going to ward off this way. Then we tuck into the front hip and go into a single whip here. Since we're all curled up like this, then we end up going out here and here at the same time, roughly. Step out, turn around while shifting the weight. Then, this is the fun one. So we come in, twist the body down. We basically are grabbing the back of somebody's calf, coming up and doing a kick here. Step out, do a kick here, or a knee. This is also potentially a block. And then, this is the part that I learned today. So, this comes down. We are bringing this hand and this hand. This hand's coming around here, and this one's coming out for basically a slap around the face or going for the eyes or something like that. So we come from here. Is it out this way or is it out this way? I think it's a hook, and we kind of back up. Then from here, this is the weird part. From here, we do a rollback, and then come back in, hands crossed, and then we slip under, pop, and then foot comes up as well. And then we're going to end up doing the same on the other side, but it's what we got for today. So this is the same Tai Chi Chuan that was the inspiration for the game Nine Souls. Highly recommended if anybody's interested in either the game Nine Souls or doing Tai Chi Chuan. It is a, if you got the right studio, if you got the right instructor, it's brilliant. You don't really want the, like, Tai Chi in the park sort of thing, if that's what you're looking for. Or unless that's what you're actually looking for. You probably want the, slightly more combative martial art. Like push hands is one of the other things that we do. So more or less you stand against somebody like this. Their forearm and your forearm are connected, and then you kind of move back and forth a little bit. Try to like press the other person off of their stationary location. Or you can get more dynamic, and then you're doing stuff like moving around while trying to knock them off balance, and they're trying to do the same to you. Okay, which of the following infinite series converge? this is just the same. We get a 1, a 2, and a 3. Number 1 says we're taking the sum as I goes from 1 to infinity of cosine to the 4th of arctan I all over n and I times the 4th root of I. Sum I goes from 1 to infinity. Nope. 2 to infinity of 1 over I natural log I. Or 3, I goes from 0 to infinity of I plus 1 cubed over 5 I plus 2 I plus 3 I plus 4. And again, as per usual, A is 1 only, B is 1 and 2 only, C is 2 only, G is 1 and 3 only, and E is 2 and 3 only. Okay. The denominator in this first one is I raised to the 5/4 power. So here we have a p-series with p in the denominator being less than -1, right? So here, or the power in the denominator is greater than 1, or the p-value, if you're just like, okay, we're doing the sum of I to the p, right? Our p-value is less than 1, so therefore it will converge. All the rest of this stuff up here is window dressing. Doesn't matter one bit. The value of cosine will be hard limited between -1 and +1, and since it's to the 4th power, it's going to be hard limited between 0 and 1. And so because of that, our values are going to be fluctuating a bit as they go on, but it's not going to affect whether or not a p-series is going to converge. Right, so 1 converges. Converges by p-series. Okay, number 2. Roman numeral 2. In this particular case, we can look at this and say, that is going to be interesting, isn't it? Our natural log is always going to make this grow slower than any 5 finite value of I to the p. So then the question is, does it actually converge, or is that just going to is it going to technically diverge because it's of the family 1 over I, harmonic series? It isn't. Like, I know it's going to right. Right, if we just look at I compared to the natural log of I by itself, I is always going to be greater than the natural log of I, and therefore I squared is always going to be greater than I natural log I. Which means that 1 over those things is going to reverse the inequality. So 1 over I squared is always going to be less than I natural log I. That's not helping me, actually. Oh, 1 over that. Jeez. I mean, not that it helps me argue anything that I want to argue, but right, so let's look at this. 1 over x squared compared to 1 over x natural log x. Right, it needs to be bound, and it's not at the moment. Hey Silver, how's it going? We're looking at which of the following infinite series converge? We already proved the first one does because it's just a p-series disguised with this cosine to the fourth, but nonetheless, it is always going to be less than or equal to that particular p-series, I to the 5/4. I index, not I being the square root of -1. All right, then the second group was, what about this one? So here, we have not been able to show yet that it converges. We have not been able to satisfactorily show that any particular power, I to a particular power, is always going to be greater than, 1 over I to the p will always be greater than 1 over I natural log I. Right? It's always going to be smaller than any particular value we care to add in here. I mean, not always, but that's part of the problem, is that in theory, right, our, what do we call those? The exponentials always end up, those aren't exponentials, sorry. The powers will usually have some intersection point with I natural log I, right? Depending on where it might be, that's a little bit different, but give us a minute on that one. Then this one ends up being equivalent if we were to make this ratio test. Actually, that's a terrible one. Ratio test limit as I goes to infinity, we end up with 1. So this is inconclusive. What other ones do we usually use here? Oh, right. So we could just say, all right, try, or we can do comparison, right? Take the limit as I goes to infinity, and then what's going to happen? Well, we know that I plus 1 raised to the third is going to be greater than I raised to the third. And we also know that I plus 2, I plus 3, I plus 4 is going to be greater than I cubed. So if we just approximate, like, what is this going to be as I goes to infinity? The ratio of this thing ends up being this, like, infinity cubed over 5 times infinity cubed. So the fraction will tend toward 1/5, which is not 0. It's not even comparison, I suppose, but so this one does not. Is this why Calc 2 is your lowest? Yeah. I taught it for a few times. It helped. All right, so as this goes to infinity, right? A sub I limit as I goes to infinity of just the terms themselves is going to 1/5, which is not 0. So the series diverges. All right, that is conclusive. So over here, when we go to this, we say, okay, number 3 is not going to converge. Okay, so let's look at this over here. Right, we know that x ln x is going to be larger than x squared. Yeah, right. Because you're supposed to. We're supposed to pick a convergent series which will always be above 1 over I natural log I. Since it's always above and it's convergent, it's bounding 1 over I natural log I, and it can't end up getting out. Therefore, it must be convergent as well. So I'm not seeing that here, right? This does not. It does not bode well, really. So, well, that's somewhat frustrating there. Okay, let's come back to that. We got 1 certainly will converge. Okay, so 42, this is the last one on this page. There's probably a good chance this is the end of my night figuring this out and then maybe doing the last one too. Find, unless anybody else has any questions. Find the smallest value of b such that the following statement is true. If 0 less than or equal to a less than b, then the series I goes from 1 to infinity of I factorial squared times a to the I over 2I parentheses factorial converges. Find the smallest value of b such that the following statement is true. I think we want a ratio test. Right, this is going to be I plus 1 parentheses factorial times a to the I plus 1 all over 2 parentheses I plus 1 factorial over I factorial a to the I over 2I parentheses factorial. Okay. I plus 1 factorial over I factorial times a I plus 1 over a to the I times, those are going to flip around, so we get 2I factorial over 2 parentheses I plus 1 end bracket okay, and again, all of this should be limited. I goes to infinity. Okay, I plus 1 times a to the first times I parentheses factorial should just be start at a number that's twice as high. No. That's double exclamation point is the thing that I was thinking of. Right. Interesting. Nathaniel Green from Yeshiva University wrote a paper on generalizing the notation for factorials to being like a factorial subscript b being the step. So if it was 2, like 5 factorial 2 sub 2, then it would be 5 times 3 times 1. But also it could include stuff like half. So 5 factorial sub half would be 5 times 4.5 times 4 times 3.5 times 3, etc. Termed by Paul Eckhart, chairman of mathematics department from Carmel High School, who called it the fractional factorial. I like it. Might not be entirely useful, but b is just the upper bound of a, yeah. So we just need to figure out what the largest value for a could be such that this thing converges, which is not terrible, right? Because this is going to say we get the limit as I goes to infinity. This is going to be right, so 2 factorial over 2i factorial divided, come on now, divided by 2i plus 2 parentheses factorial says that we're going to get rid of everything in the top, and down bottom we should have 2i plus 2 and 2i plus 1. Those are the only things that are different. Okay, this is also just 2 parentheses I plus 1, which will divide out with this one. So the limit as I goes to infinity of a over 2 parentheses 2i plus 1. Right, that is a finite number. Wait. I didn't do the thing, did I? Oh, I did not do the thing. Hey, Zach. Yeah, we're doing all right. I just screwed up. It kind of matters this time. A lot of times it doesn't. This time it did. That squared right there, I did not put in to all this. So this is going to be a square here. Wait. Inside? No, outside. Well, I mean, that's a good piece of news, I suppose, if we're talking about this in terms of there's 2 of those. we get rid of one of them with this one here in the denominator directly. This is I plus 1. Okay, this is actually, this is fine. So no, I just use I for an index, which I know is terrible because it has a different other context, so it gets to be difficult when you're like, oh no. Okay, so this is I plus 1. On the bottom, this is 4I plus a half. And if we're doing limit as I goes to infinity, then these two are effectively equal to each other. Again, they're so close that it doesn't really matter. They're just going to divide out as I goes to infinity. So this is saying that this is going to be A over 4 needs to be the limit as I goes to infinity of all that stuff up there, which is capital L. So A must be less than 4. So B equals 4. All right, the actual stuff that we did not copy down. Values that were used to calculate various things. A was 1. B was 2 ln 2. C was 2. D was 2 root 2. And E was 4. I think we have our winner. Oops. How about this one, Zach? Which of the following infinite series converge? So we got the first one is going to converge by P series, a simple comparison. The numerator is not going to matter. It's just between 0 and 1. So all of our individual values here are going to be less than or equal to 1 over I to the 5/4. No worries. Number 3 is going to end up with a ratio test of 1, so that's not helpful. But we can compare both top and bottom to I cubed, which is going to divide out both things. Again, as I goes to infinity, we end up with 1/5, which means that even this series doesn't go to 0. So it diverges automatically. So this failed. The second one I'm having a little trouble with. So what's the sum as I goes from 2 to infinity of 1 over I natural log I? I tried comparing it with just I squared, but I squared is lower than it. So we can't say anything definitively. Integral test? That's probably a good one. Oh. Yes, thank you. All right, as we're going to start, I might as well just run that real quick. So be back in 3. Thanks for coming, everybody. How we doing, YouTube? Nobody else can hear me. 5 seconds till my Twitch chat says we can hear you. Come on, Obi. Go from 2 to infinity. 1 over x natural log x dx. Where let u be equal to natural log x du equal 1 over x dx. Yep, okay. This is x is going from 2 to infinity of 1 over u du. Yay! natural log u. X goes from 2 to infinity. U is natural log of x, so this is going to be the natural log of x as we go from 2 to infinity. Right. I mean, looks like it diverges to me. So limit as b goes to infinity of natural log b minus natural log of 2. So this is going to go to infinity minus natural log of 2, which is finite, so this is just going to be infinity. So it appears that number 2 diverges, which would mean 1 only, which would mean A. All right, now let's make sure I didn't do anything wrong here. Yeah. So the intuition that I had before there is no p-series such that I to the p is going to be sum. I goes from 1 to infinity. Such that sum of all I to the p's is going to be greater than sum of 1 over I natural log I for all I in positive integers. There is no convergent. So p less than -1 in this particular setup. So the intuition was that, you know, if we pick the harmonic series 1 over I, then it's divergent in the first place. And then if we pick any other value for p, so less than -1, where it is convergent. So p is -1.0000001, that eventually the natural log will still go through that particular value. So no matter what you do for p, we're always going to be able to find some natural log value, you know, I natural log I, which will eventually pass through whatever p series you came up with. So, oh well. Okay. I think that's good for tonight. We're getting a little tired, and we're done with yet another page. Next week, hopefully I can catch a nap or something beforehand, and then we can go a little extra long and finish problems 43 through 50. Because we're getting there. So, let's go find somebody. Let's see if we got anybody for... Yep, Danny Anduza's doing some paleontology news. Let's go see Coco Confession. She is one of the GoTel members, and we'll go say hi and let her know how we're feeling. So, hope you all have a good rest of your night. I'll be back tomorrow for TTRPG planning. We're working on Titan's Grave. We're doing all right. My players made it through their first actual real threatening meat grinder last week. They almost died. We almost had a party wipe. So it was getting a little touch and go there for a while, but they figured it out. If only one of them wasn't a kleptomaniac, and if only the others had listened to each other a little bit, they would have figured out the secret of getting through this dungeon, and probably, honestly, they probably would have steamrolled the guys. Oh well. All right. See you all tomorrow for TTRPG planning, and then we'll see if we can come back on Friday for probably Baldur's Gate 3. We'll see how things are going. And hope to see you all soon. My name is Obi-Wan Pez. This is Ensign Blex Pachinko. Catch you next time.